Hello everyone, my name is Yahan. I'm a postdoctoral researcher in TU Delft, working within the Zoom lab. Today I'm excited to show some findings from our recent research titled Integrated Optimization of Demand Management and Timetabling or an Urban Transit System Abundance Decomposition Approach. As we all know, in many cities around the world, congestion in metro systems has become normal. These photos show different forms of congestion across cities and locations within the system. On the left, you can see the long queues outside the station entries in Beijing. On the right, this is the platform congestion in Shanghai. In-vehicle congestion is also a normal issue. For example, in Tokyo, passengers are packed tightly during peak hours. In New York, the figure shows how difficult it can be to get on the train when demand far exceeds available capacity. There are several strategies used in real-life operations to reduce the congestion. The first one is increase frequency from the supply side. The second one is implement passenger flow control policies from the demand management side. For example, Beijing and Shanghai in China has already implemented this policy. The third one is to implement the trip reservation policy from the demand management side. For example, Beijing and Chongqing Metro in China has already tested this strategy. There are several technical details for this for the trip reservation policy. The first one is that reservation slots are released to the public the day before operation. The second one is the number of slots is limited. The third one is reservation is free and can be done through mobile applications. And in Beijing, it has received a remarkable 88% favorable passenger feedback. There are several research gaps in the literature. The first one is that in practice, the demand management strategies and timetables are developed independently and subjectively based on the experience of operators. In the literature, most of existing approaches are limited to addressing train timetabling, passenger flow control, dynamic pricing, and trip booking problems either separately or only partial integration. Moreover, they typically rely on heuristic measures to solve the proposed models. So what we do? We contribute to this fleet by developing a unified and generalized modeling framework for the problem that integrates the trip shifting, passenger flow control, and train timetabling in urban rail transit system with the trip reservation policy. The second contribution is that we propose a novel and generalizable decomposition framework tailored to the mathematical structures of our problem. The third contribution is that we validate the proposed methodologies through the both proof of concept and real-life case studies. The results show considerable improvements in operational efficiency and service fairness, fleet size, and congestion levels. The final contribution is that on the algorithm side, the proposed solution framework shows strong computational performance. Now let's dive into the problem description part. In our problem, we optimize the timetabling. That means we optimize the arrival and departure time of each train at each station. The second thing is that we optimize trip shifting policy. In the context of trip shifting policy, the passengers who have flexible arrival time, especially for the passengers who can arrive at their destinations during peaking hours, they are encouraged to shift their arrival time, shift their departure time at the origin station from the peak hour to the non-peak hour, and we will give them some discounts on their tickets to encourage them to the trip shifting. The third thing we optimize is the passenger flow control strategy. The passenger flow control represents the number of passengers without reservation who board each train at each station. In our problem, the passengers who have successfully made reservations can directly board the coming trains without the need of waiting for the permission from the passenger flow control policy. So in our problem, the operators determine the optimal operational strategies under varying levels of government subsidy and provides the government with a set of feasible and efficient solutions. The government plays an important role by providing the subsidies to the metro company to ensure that the company can encourage passengers to shift their trips. Under our demand management policies, there are three types of passengers. The first type of passengers includes those who have successfully made reservations. If they have made a reservation, if they have successfully made a reservation, they can arrive at the original station with the scheduled time, and they have to pay for the full ticket price. The second type of passengers are those who try to make a reservation but falls due to the limited number of reservation slots. For those passengers, if they choose to arrive at the original stations with respect to the suggested time by the our reservation system, they can enjoy a discount on their ticket price, but they have to wait for the permission from the passenger flow control policy. The final type of passengers are those who freely arrive at their original stations. They need to queue outside the station entries and pay for the full ticket price. In our modeling framework, our objective is the sum of total waiting time and detained time of passengers, and the extra subsidies paid to the metro company for encouraging passengers to shift their trips. Our decision variables are three types. The first one is the number of the number of passengers without reservations who traveling from station U to V and shift their departure time from their scheduled time. The second type of decision variables is the number of passengers who without reservations who head to station V and are allowed to board train I at station U. The third type of decision variables is the train timetabling decision variable. To solve this complex problem, we aim to use the exact algorithm to provide the exact solution, to provide the high quality solution with guaranteed quality. So we use the bundle decomposition to solve this problem. However, the traditional decomposition method for the timetabling problem with passenger assignment would typically decompose the problem as a train timetabling subproblem and passenger-oriented optimization subproblem with fixed timetables. In the results part, we will show this traditional decomposition method is not good enough to solve our problem. To address this issue, we propose a novel decomposition method where we decompose our problem into a timetabling subproblem incorporating full information about passengers with reservation and partial information of passengers without reservations, and a passenger flow control optimization subproblem. Through our solution method, we can reduce many iterations of generating relatively weak feasibility case and improve the lower bound in the first few iterations. We validate our modeling framework and solution method through two sets of experiments. The first set of experiments is based on a metro line with 6 stations. The key finding is that encouraging about 21% of passengers to shift their departure time by up to 10 minutes through providing the discount on tickets would result in savings at least 8.33 points in the number of needed trains at the cost of about 2% increase in subsidies. Then we validate our solution measures and modeling methodologies in instances based on Beijing Metro bottom line. We design 6 variations of our solution method. The first one is the band decomposition, which have the optimality and feasibility case. The second one extends the band decomposition by including the loop, some heuristic speed up techniques. And the results show that the TTCBD measures outperforms the other 5 variations of band decomposition measures and also Groby. In this figure, we can see that TTCBD outperforms the other algorithms without the tree search strategy, and the Groby band decomposition and TCBD can quickly find a good upper bound, while the lower bound slowly increase. Finally, we compare our algorithm with 2 benchmarks. The first benchmark is a hybrid algorithm combining a local search method with Groby. The second benchmark is the traditional band decomposition algorithm, where the master problem only determines the timetables. The goal of this set of experiments is to address the following questions. The first one is, to what extent does TTCBD outperforms the hybrid algorithm? The second one is that to what extent does TTCBD outperform the traditional band decomposition? And we can find that even for the smallest instance among the 4 instances, for example, the instance J, the hybrid algorithm can only find a solution with 10% optimality gap. This result highlights the advantages of using exact measures and our decomposition framework to solve the problem. From this figure, we can observe that considering both the computation efficiency and the best upper bound, our developed TTCBD algorithm outperforms the other benchmark solution measures. Finally, we compare our integrated optimization approach against the 2 benchmarks. The first one is the PFC method. In this method, we optimize the passenger flow control policy without allowing for trip shifting under the optimized train timetable through our integrated optimization approach. The second benchmark is SPE. SPE means the simulation represents the simulation method. That is, we simulate the evaluation of passengers under the same optimized train timetable. and the results show that upon inputting the timetable into the PFC and FPE measures, both models are proved to be infeasible. This results shows that in the absence of trip shifting policy, the existing number of trains are incapable of satisfying all passenger demand. That means our integrated optimization approach can save the number of used vehicles for operations. In sum up, we formulate a model for the integrated optimization problem of trip booking, trip directing, and train timetabling. We design a tailored decomposition framework and abundant decomposition-based solution algorithm. We show the benefits of the integration and the solution measured in real-world cases. For the details of this paper, we invite you to scan the code to see our earlier preprint version. In addition, we have also explored the exact solution measured in the robust optimization problem. That is, we use the exact algorithm to solve a robust charging station location and routing scheduling for electric modular units. If you are interested, please scan this QR code and to have a look at our preprint version. Thanks.